Good morning, students. Our next theorem is, for a group G, we have a sequence of subgroups of G, which is denoted by gamma ig. Here, I is greater than or equal to 1. This is lower central series for the group G. Then, we are to prove that the commutator of the member gamma ig with gamma jg, that is contained in gamma I plus jg for every I and j which are greater than or equal to 1. To prove this result, let us apply induction on I. So first of all, let us take I is equal to 1. For I is equal to 1, the left hand side becomes the commutator of gamma 1g with gamma jg. Now by definition of lower central series, gamma 1g, that is defined as g. So this becomes commutator of group G with gamma jg. Now again, by definition of lower central series for the group G, the commutator of group G with gamma j, that is defined as gamma j plus 1, and this is contained in itself. So we have proved that the commutator of gamma 1g with gamma jg, that is contained in gamma 1 plus jg. So this proves the result for I is equal to 1. So this completes the first step of induction. Now, in the next step, let us assume that I is greater than 1 and the result is true for every k which is less than I, such that commutator of gamma kg with gamma jg, that is contained in gamma k plus jg. Here j is greater than or equal to 1 and k is less than I. Now, to complete the induction, let us use 3 subgroups lemma of P Halls. To use that lemma, let us consider the 3 subgroups of G. First G itself, second gamma jg, and next gamma I minus 1j. Now let us find the commutator of G, gamma j and gamma I minus 1. Now by definition, the commutator of 3 subgroups of G can be written as the commutator of G with gamma j, then its commutator with gamma I minus 1. Now by definition of lower central series, this is gamma j plus 1. So this becomes the commutator of gamma j plus 1 with gamma I minus 1. Now by using the induction step, this is contained in gamma of their sum I minus 1 plus j plus 1, and this becomes gamma I plus j. So we have proved the commutator of G, gamma j and gamma I minus 1 is contained in gamma I plus 1, gamma I plus j. Now let us consider the commutator of gamma j, gamma I minus 1 and g. Now by definition again, this can be written as the commutator of gamma j with gamma I minus 1 and then its further commutator with g. Now again, this commutator is contained in gamma of I minus 1 plus j. So this whole commutator that will be contained in the commutator of gamma I minus 1 plus j with g. Now this can further be written in this way, and this is gamma of I plus j. Now let us denote this subgroup of G by M, because we already discussed all the members of lower central series, they are normal in G. So gamma I plus j, that is normal subgroup of G. Now we can apply three subgroups lemma P Hall. So by that lemma, the commutator of gamma I minus 1, G and gamma j, that is contained in this normal subgroup M. M is gamma I plus j. Now this can further be written as the commutator of gamma I minus 1 with the group G, and then its further commutator with gamma j, and this is contained in gamma I plus j. Now again, by definition of lower central series, this commutator is gamma I. So we have obtained commutator of gamma I with gamma j is contained in gamma I plus j. So this completes the induction. So we have proved that the commutator of gamma I with gamma j is contained in gamma I plus j, and this is true for every I and j which is greater than or equal to 1. Now our next theorem is for the upper central series. Let us take G is a group and Zij, where I is greater than or equal to 0. This collection denotes the upper central series for group G. Then we are to prove that the commutator of Zm with gamma n, that is contained in Zm minus n, and this should be true for every m which is greater than or equal to n, and this is further greater than or equal to 1. To prove this result, again we use induction on m plus n. So first of all, let us take m plus n is 2. Now because m is greater than or equal to n and this is further greater than or equal to 1, so we must have m and n both are 1. Now left hand side becomes the commutator of Z1G with gamma 1G. Now by definition, gamma 1, this is the group G, so we get commutator of Z1G with G. Now Z1G means center of group G, so this becomes commutator of center of G with group G, and that is contained in identity. And by definition of upper central series, this is Z not G. So we have proved the commutator of Z1G with gamma 1G is contained in Z not G. So our first step of induction is complete. We have proved the result for m plus n is equal to 2. Now let us assume that m plus n is greater than 2 and the result is true for all I and j having the sum less than m plus n. Here I is greater than or equal to j and this is further greater than or equal to 1. Now again we are to use three subgroups lemma of P Hall. So let us consider three subgroups of G. First one G, second gamma n minus 1, and next Zm. Now let us find the commutator of G, Zmg and gamma n minus 1 G. Now by definition, this can be written as the commutator of G with Zmg, then its further commutator with gamma n minus 1 G. Now by definition of lower central series, G can be written as gamma 1G, and this commutator can further be written as the commutator of ZMG with gamma 1G, and then its further commutator with gamma n-1G. Now, because the result is true for every I and j such that I plus j is less than m plus n. So, by induction step, this commutator is contained in Zm-1J. So, this whole commutator will be contained in the commutator of Zm-1G with gamma n-1J. Again, these two suffixes are having the sum less than m plus n. So again we can use induction step. So this commutator will be contained in Z of their difference, which is m minus n. So we have proved the commutator of G, ZMG and gamma n-1G is contained in Z m minus n G. Now let us again consider the commutator of the three subgroups of G. First one ZMG, second gamma n-1G, and third the group G. Now again this can be written as the commutator of ZMG with gamma n-1G, and then its further commutator with group G. Now, the sum of these two suffixes is less than m plus n, so we can use induction step. So, this commutator is contained in Z m minus n minus 1G. So, this whole expression is contained in the commutator of Z m minus n plus 1G with gamma 1G, because gamma 1G is same as G. Now, this commutator is further contained in Z m minus n plus 1 minus 1G. So we have proved the commutator of ZMG, gamma n minus 1G and the group G is contained in Z m minus n G. Now let us denote this subgroup of G by M. All the members of upper central series, they are normal in G. So M is normal in G. So we can apply three subgroups lemma of P Halls. So by that lemma, the commutator of gamma n minus 1G, group G and ZMG, that is contained in Z m minus n G. Now this can further be written as the commutator of gamma n minus 1G with gamma 1G, then its further commutator with ZMG. Now by definition of lower central series, this commutator is gamma NG. So we get commutator of gamma NG with ZMG is contained in Zm minus NG, and this can further be written as the commutator of ZMG with gamma NG. So we have proved commutator of ZMG with gamma NG is contained in Zm minus NG. So this completes the induction and the proof. Now our last theorem in this section is to prove that subgroup of finitely generated nilpotent group is finitely generated. So let us take G is finitely generated nilpotent group having the nilpotency class C. So by definition of nilpotent group, G will have a central series. So let us take the central series for the group G given by G is equal to gamma 1G contains gamma 2G, contains gamma 3G, and so on, contains gamma C plus 1G. Gamma C plus 1G is identity, but gamma CG will not be equal to identity because the nilpotency class of group is C. Now, the factor group gamma I by gamma I plus 1, that is finitely generated because due to this result, if group G is generated by a set X, then the factor group gamma I by gamma I plus 1, that is generated by the elements of this form. Here, these elements x1, x2, x3 and so on up to xi, these are the elements belonging to the set X. Now because here the group G is finitely generated, so the choices for these elements are finite, and because this factor group is generated by this type of elements, so we can say that this factor group is finitely generated. Also, this factor group is abelian. Now, to prove our result, we are to prove that subgroup of finitely generated nilpotent group is finitely generated. So let us take a subgroup of G. We have denoted it by H. We are to prove that H is finitely generated. To prove this, let us define for every I varying from 1 to C plus 1, we define the members Hi by taking the intersection of H with gamma Ig. Now, for I is equal to 1, this will become H1 and this will become H intersection gamma 1G. Gamma 1G is G, so H intersection G will become H. Now for I is equal to C plus 1, we have HC plus 1 is the intersection of H with identity. So that is identity. And also by definition of lower central series, each gamma I plus 1 is contained in gamma I. Taking intersection with H on both sides, we get Hi plus 1 is contained in Hi. And this is true for every I varying from 1 to C. Also, each Hi is normal in H. And this is true for every I varying from 1 to C plus 1. Now, let us consider the factor group Hi by Hi plus 1 and putting the values of both Hi and Hi plus 1. Now, gamma I plus 1, that is contained in gamma I. So, gamma I plus 1 can be written as gamma I intersection gamma I plus 1. Now, this can further be written in this form. Now, using this theorem, A by A intersection B is isomorphic to AB upon B. So, this will be isomorphic to H intersection gamma I into gamma I plus 1 by gamma I plus 1. This intersection is contained in gamma I. So this factor group is contained in the factor group gamma I to gamma I plus 1 by gamma I plus 1. Now, this is further contained in the factor group gamma I by gamma I plus 1. Now, this is finitely generated abelian group, and subgroup of finitely generated abelian group is finitely generated, and therefore this factor group Hi by Hi plus 1, this is finitely generated, and this is true for every I varying from 1 to C. So in particular, for I is equal to C, from here we get the factor group HC by HC plus 1 is finitely generated. Now this HC plus 1 is identity. So this factor group is isomorphic to HC, and this is finitely generated, implies that HC is finitely generated. Also, the factor group HC minus 1 by HC is finitely generated. HC is finitely generated. So we can say that HC minus 1 is also finitely generated. So we can continue like this to prove that H is finitely generated. So this completes the proof of the theorem that subgroup of finitely generated nilpotent group is again finitely generated. And this completes your section 1. Tomorrow we will start the section number 3.